Today I would like to talk about specific heat and latent heat. Here I will show two examples. Before getting into this heat episode, before getting into the topic, we can have mainly two equations. One is Q is equal to mc dt. This is for the temperature change. That means heat absorbed or released when there occurs a temperature change. So here there is no phase change occurring. Only thing is happening is change in temperature. So here Q is the heat energy absorbed or released by this temperature change. M is the mass of the substance, C is the specific heat of the substance, and dt is the change in temperature. So dt actually its formula is this one: final temperature minus initial temperature. And the another equation for the heat energy absorbed or released is it is during a phase change. So at that time there won't be any temperature change. So there will be phase changes, and at the time of phase change there will be um, heat energy absorbed or released, and that is represented by Q is equivalent to ml, and m is the mass of the substance and L is the latent heat. Now let's have a look at the first example. So here what we are considering is ice at a temperature less than 0 degrees Celsius. Say we are taking it as T1. It is added to a copper container, and the copper container is holding water, hot water, and its temperature is less than 100 degrees Celsius. Uh, Let it be T2. So, in this scenario, we are analyzing how much heat energy is absorbed or released at each stages, because this ice converts to otherwise there occurs step by step changes, so we can analyze each steps. Actually there occurs 5 steps here. So first of all, once we get such a problem, what we have to look is our system. What are the components of our system? Otherwise, yes, what are the components of our system? Our system consists of ice, and its temperature is less than 0 degrees Celsius, and it is termed as T1. Then copper at a temperature of T2 degrees Celsius. Then a hot water in that copper container. It has the same temperature T2 as that of the copper. Then our aim is to make all these components, otherwise all these items in our system, that is ice, copper and hot water, to an equilibrium temperature T3. We have to make all these things into an equilibrium temperature T3. That is our aim. And first thing is ice at a temperature less than 0 degrees Celsius, that is T1 degree Celsius. So first process is ice warms, that is ice absorbs heat energy from the hot water and then it warms to um, 0 degrees Celsius. That there occurs a temperature change. Ice at minus 10 degrees, ice at T1 degrees Celsius changes to 0 degrees Celsius. So which is the final temperature? 0 degrees Celsius, and which is the initial temperature? It is T1 degrees Celsius. So Q1 will be mass of the ice, specific heat capacity of ice, into final temperature is 0 minus initial temperature is T1. Then that is what I have described here. So this is the first process. Then the second process is ice melts. That means 0 degree Celsius ice changes its phase to water. So at that time there won't be any change in temperature. That is ice at 0 degrees Celsius changes its phase to water at 0 degrees Celsius. So the process is melting of the ice. And here the heat energy absorbed or released, here it is absorption. So heat energy absorbed is equivalent to mass of the ice into latent heat capacity of the ice. This we already said, this is the formula for the phase change. Then the third step, third process, otherwise we call as third process, is water that was ice bombs. Water which was ice initially, sorry, okay, water that was ice it warms. It again warms to an equilibrium temperature T3. So these three steps constitutes the changes for the first component, that is ice. So in this step, water at temperature 0 degrees Celsius changes its temperature to T3. It is an equilibrium temperature. So here there occurs a change in temperature. So the heat energy absorbed is equivalent to mass of the ice into, here it is a specific heat capacity of the water. That is because of the reason it is the water which changes the temperature. That's why we are taking as a specific heat capacity of the water. And why we are taking it as ice? Because initially it was ice, the component was ice, and it is that ice melts into water, so it is equivalent to the mass of the ice. So mass of the ice into specific heat capacity of water into this T3 is the equilibrium temperature, that is the final temperature achieved by that component, minus 0, because that is the initial temperature of the water, because water at temperature 0 degrees Celsius, so that is the initial temperature. So that is what mentioned here, m mass of the ice, specific heat capacity of water, then final temperature T2, initial temperature T3. Now the second component of our system is copper. So what happens to the copper? Copper is already at a temperature of T2. So it has to convert into a temperature equilibrium, which is equilibrium. So copper changes its temperature from T2 to T3, that is T2 to T3. So here there occurs a temperature change. So the equation we have to use is Q5 is equivalent to mass of the copper, specific heat capacity of the copper, T3 minus T2. T3 is the final temperature and T2 is the initial temperature. Now again, oh, we missed one thing, Q4, that is before Q5, because what there is already, we told that there is a three components for the systems, and the one component is hot water. So hot water must cool from T2 to T3. Hot water must cool from T2 to T3. So it is also a temperature change. So the equation will be of the form this one. Q4 will be equivalent to mass of the water, specific heat capacity of water, into final temperature is equilibrium temperature. T3 initial temperature is hot water is at the initial temperature T2. So this is the thing. Here we used mass of the water, specific heat capacity of water, because here this is the hot water, not that ice. This is the hot water. That is why water for both. Then final temperature T2, initial temperature T3. This we have already told. Now the conservation of energy equation, that is total energy, sum of the total heat absorbed or released in a process is equivalent to the all the sum of the single process, that is Q1 plus Q2 plus Q3 plus Q4 plus Q5. And this is the thing, that is mass of, we are adding that each single processes, that is mass of the ice into specific heat capacity of ice into, it was initially at a temperature of T1, it changes to a temperature of 0, so 0 minus T1. Then in the second stage, this ice at 0 degrees Celsius converts to water at 0 degrees Celsius, so phase change, that is mass of the ice into latent heat of ice. Then plus the third one is the water at 0 degrees Celsius converts to a temperature of T3, that is water changes its temperature from 0 degrees Celsius to T3, equilibrium temperature. So this mass of the ice, because it is this mass of the ice that converts it into water. So both cold water as well as the ice has the same mass. And this is the specific heat capacity of water, then into T3 minus 0. Then this is the hot water, it changes its temperature from T2 to equilibrium temperature T3. Sorry. Then this is the copper, so mass of the copper, specific heat capacity of copper, then it changes its temperature from T2 to an equilibrium temperature T3. So once we add these all things, we get the equation for the conservation of energy. Now similarly, we can analyze different types of processes. So the another process for which we are not analyzing the conservation of energy equations, we are just saying what happens to this process. So this will be ice to water transformation. here what we are considering is, first we are considering an ice at minus 10 degrees Celsius. So what happens first? It changes its temperature as initially. It changes its temperature and converts to ice at 0 degrees Celsius. So there occurs a change in temperature. Then there occurs a phase change. Ice at 0 degrees Celsius converts to water at 0 degrees Celsius. So there occurs a change in phase. Then there occurs a change in temperature. Water at 0 degrees Celsius converts to water at 100 degrees Celsius. So here we stops because here we are considering up to 100 degrees Celsius only. Thereafter there is some process called evaporation. We are not mentioning at this stage. Thank you.